All right, hello everybody. This is the practice exam 3 solution commentary. First, I'm just going to talk a quick bit about the forward and strategy slide, which I threw on here. I'll also talk about it in class during my review session. So the hardest thing in thermo is not knowing which of the many similar looking equations to use. So a pretty good strategy that can help you orient yourself is if you look for some keywords in the questions, which sort of restrict the number of equations you might have to sift through. So some keywords are isothermal, isobaric, isochoric, and similarly adiabatic. When those words are stated, it tells you something about what variable was held fixed during a process. And because of that, either Charles' law, Boyle's law, or the Gay-Lussac law will apply to those compressions. Also, the first law, except for isobaric compressions, usually simplifies a lot. For instance, when a process is isochoric, work done is zero, so the first law loses the work term and it becomes very simple. And even if it's not isochoric, even if the work isn't zero, if it's isothermal or isobaric, if it's isothermal or isobaric, the work done during the process is easy to calculate. It's listed on the equation sheet. If it's isobaric, it's just minus P delta V because P is a constant. And if it's isothermal, you have to do the integral of the 1 over V dV thing, and you get that equation with the log of V final over V initial. For adiabatic systems, the equation that's sort of like Boyle's law that you're allowed to use is like the one with PV to the gamma initial is P final, V final to the gamma. And you can also use the alternative forms where you substitute T instead. So it's like, what is it, TV to the gamma minus 1 or something like that. Also, adiabatic means for heat input is 0. So the first law is also going to simplify because one term just drops out. Next class of keywords will be if the question tells you a gas is mono or diatomic, even though you haven't been told it directly, CV and gamma are known constants for all mono and diatomic gases. So you actually know those values even though it didn't get told to you in the question. If a question asks about the ratio of the final pressure to initial pressure, or it tells you the ratio of the final volume to the initial volume and asks about something, and it's something you can do. It's equivalent to Boyle's law, so like you might not actually have to rederive it. But it might be smart to take 2 copies of either the ideal gas law or E equals K, like number of degrees freedom over KT, or times KT, and divide it by itself. The final copy of the equation for the variables at the end, and then another copy with the initial variables. And dividing the two can sometimes give you that T final over T initial expression that you need. If a question talks about heat, it almost certainly is going to involve the first law, if it's not a calorimetry problem, which is sort of the first law anyways. So you probably are going to want to use the first law to find the heat in a process, although there are some shortcuts. For thermal energy, or the change in thermal energy, you want to use the either MC delta T or N capital C delta T for the change in thermal energy. Or for this weird class of question, which is kind of different than the rest, where it asks about the absolute thermal energy, you can use the number of degrees of freedom over 2 times Boltzmann constant times temperature. But like I said, that's pretty separated from it. Most of the time, you're going to be using NCV delta T in like your first law or whatever problems. If something is freezing or melting potentially in calorimetry, you want to put in the plus minus latent heat times mass terms, not just the MC delta T terms. So it doesn't really complicate the problem that much, but you just need to remember to put them in with the appropriate sign, which I list in the equation sheet. And lastly, if there's an engine, don't try and shortcut it. Draw the engine diagram of the 2 reservoirs and work out. Same for the refrigerator. That'll just help you avoid stupid side mistakes. All right, so let's get to the questions. Okay, immediately I see one of my keywords, isothermal. So I know either like the Charles law or Boyle's law or whatever might apply. So let's see, I'm told volumes and initial pressure, and I'm wondering what's the final pressure. And isothermal was my keyword, so I immediately think, oh, maybe I could look for Charles' law. So let's see, in our equation here, Charles' law, says it applies when, Boyle's law is isothermal. So on the equation sheet, I have P final, V final equals P initial, V initial. Okay, I'm told every variable but one, so this problem is going to be pretty easy. Let's see, I'll move everything over. So I'm looking after P final, so I'm going to get it by itself. Okay, and now I just substitute in variables. P initial is 400,000 pascals. V initial is 2 meters cubed, right, because it's compressed from 2 meters cubed. And V final is 1 meters cubed. So this gives me 800,000 pascals. Just double check that I'm recording. Okay. A small amount of ice is placed in a large amount of water. So I'm going to sketch a picture really quick. It's a tiny, tiny amount of ice. It's at negative 33 Celsius. And all the water is already at the freezing point perfectly. So what happens when there are two objects of different temperatures touching is heat flows from the hotter object into the colder object. Hold on. Let me just solve this one and then see if I can reverse explain the answer. This one, I knew this one was going to give me a problem explaining it when I did it. So the water is already at the freezing point, and the ice is well below the freezing point. So as they try and sort of give energy to each other, the ice is actually going to. Oh yeah, okay. This is what's happening. Sorry. The ice is at a much lower temperature than the water. So the water is going to give some heat, some of its heat to the ice to try and heat the ice up. Now the ice isn't perfectly at 0 Celsius. It isn't about to start melting. So what happens is the water is going to use some of its heat. It's going to give off some heat. Okay, and the heat is going to go into the ice. So the water was already about to freeze. So as it gives off a little bit more heat, it actually starts to freeze a little bit. And then meanwhile, the ice's temperature goes up until everything is the same temperature, which since there's such a large amount of water, the ice will be able to freeze a little bit more water, but the rest of the water is still going to be sitting there at 0 Celsius. And the ice is going to keep going until it is also at 0 Celsius. So the final picture is pretty much the same thing with a little bit more ice frozen, and everything, the water and the ice, is at 0 degrees Celsius. Okay, this is a little bit of a mind bender question, but it is worth understanding. Okay, there's a lot of words on this slide. A substance's melting points, boiling points, and specific heats are given. And we're bringing an object from one temperature to another. So it's going to freeze and have some specific heats going on. So let's sort of draw a picture of what's going on. Okay, so the boiling point is 150. Melting point is 20 Celsius. Okay, I start up at 170. I'm not going to write T initial. I'm going to write with a real subscript like T original, and T end is all the way down at 5. T end. And sorry, this is the melting point, not the boiling point down here. Okay, so we have a couple sources of energy going on here. We have this temperature change, so this is going to be mass times the specific heat in the gas phase, because it's a gas right here, times the temperature change, which is negative 20. I'm going to use all the I'll use the negative sign. So the temperature change is minus 20 until it gets to the boiling point. Now when it gets to the boiling point, it's going to condense. And the heat required to condense an object is given by the latent heat of vaporization times the mass, right? Q here is going to be latent heat of vaporization times the mass. Okay, after that, there is a 130-degree cool down, but at this stage, the object is in a liquid phase. Okay, then there is melting, given by the latent heat of fusion times the mass. That's how much heat it gives off or requires to melt an object, or freeze an object. The object gives off heat in that case. And then finally, in the solid phase, there is cooling by an additional 15 degrees. And I'm going to make all these heats the same sign, right? When the gas cools down, it gives off heat, and when it condenses or freezes, it gives off heat. So these are all heat outputs by the gas into the surroundings. So now it's just a matter of plugging in a bunch of numbers. So M is 0.5 kilograms everywhere. Okay, C of the gas phase is told to us to be 400. The liquid phase is 1,000. The solid phase, C, is 600. Heat of vaporization is 7 times 10 to the fourth, and latent heat of fusion is 3.5 times 10 to the fourth. So I'm just going to add up all these numbers at once here. So I have mass everywhere. So first I'm going to work top down. So 0.5 times 400 times 20 gives me, in red, this here is 4,000, or negative 4,000 depending on your taste. This right here, 7E4 times mass is 1/2 of kilograms, so 3.5 E4 joules. Again, negative sign if you want. Okay, this again, I just multiply L times M, which gives me 1.75 E4. This in the middle, 0.5 times 1,000 times negative 130 gives me 65,000. Again, I'm doing all the sizes of the heat outputs. Technically, these are all negative numbers since it's heat outputs. Okay, and lastly, solid phase gives me negative 4,500. So I'm going to total up all these numbers. I'm going to get total is negative 126,000 joules, and the negative sign just communicates heat was given off rather than intaken by the gas. Okay, we have a key word here, an isochoric process. Okay, and we're wondering about work done on the gas. Let's see. So it seems like, first law might be a good thing since we have work and thermal energy, and you can try to do it that way. But what you'd quickly realize is if you scroll to the work, or let's say if you tried to write out the first law, again, you don't actually need to do this. Okay. You'd look at your first law, and then you'd look at the keyword isochoric, and you know that the first law simplifies when you have either isochoric or isothermal or adiabatic. And if you scroll down to the first law section, first law special forms, you see isochoric, W equals 0, since the volume change of the gas is 0. And that's actually what the question is asking you about, right? Work equals 0, since isochoric means V doesn't change, which means like this either P delta V or negative integral of P dV, doesn't change, right? Volume is held constant. So the work done is zero. So this is a little bit of a trick question. Okay, a phase diagram is shown. The temperature is held at a certain number, so we're going to be very careful. Temperature being a fixed number means we never move left to right off of 100 Celsius, which is this dashed line over here. Okay, we never, ever, 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 ever move off this line, right? Because if I go to the left, that's temperature less than 100. If I go to the right, that's temperature more than 100. We decrease the pressure from 100 atmospheres, which is somewhere like here, down to 0.5 atmospheres, which is somewhere like here, if you look at the vertical scale. So you go from liquid water to water vapor, so the water boils. Very easy on this problem to accidentally go, like, to try and go left to right or something, thinking that that's decreasing pressure because you're going towards the P, but that is not how that works, right? Your vertical height tells you your pressure, and your left to right position tells you what temperature. So you're fixing your left to right position and sliding from high pressure down to low pressure. Okay, here's a qualitative question about if temperature goes up, down, or what happens. So a gas is compressed isobarically, so the pressure is constant. Okay, so we're asked about temperature. So this might be also a sealed container. I assume the volume is fixed. So we can look at isobaric, means we might want to look for like the Gay-Lussac law or Charles' law. Let's see. Isobaric is Charles' law. Hold on a second. So there's two ways I was thinking about doing this problem. Okay, P is held constant, V is held constant. Oh, sorry, I don't think it is supposed to be. No, okay, sorry. This question is written a little bit wrong. Sealed container means the piston volume is not held constant. Right, this doesn't make sense. It's a compression. That's part of the problem. Okay, so we can indeed look at Charles' law. That's why I was so confused. So Charles' law, again, I knew to look towards Charles' law because it said isobaric. It gave me information about how does the volume change. V final is less than V initial because it's a compression. And it asks me about temperature. So Charles' law contains pretty much every variable in the problem. Okay, so VF is less than VI, so this number is less than 1. We'll call it like 0.5. As a typical number you might actually get out if you were given the values. So this tells me if I multiply Ti over to the other side, that Tf is 0.5 Ti. So the temperature has gone down by a factor of 2 in Kelvin. Okay, so temp in Kelvin is halved. And this sort of makes sense. If you squeeze the gas down, it's going to try and push harder. So if you need to cool it down in order to keep the pressure constant. So that sort of makes sense intuitively. Okay, so we're talking about average thermal kinetic energy, so like the absolute thermal energy, which is given by this equation here. And there's a couple ways you can do this. If you want, you can plug in some constant k in for curly E, and you can find the value of the group of constants E divided by KB times 2 over number of degrees of freedom, and then plug that in later. Or the way I would do this problem is one of your emergency processes is if you're told an initial and a final, you should take 2 copies of the equation and divide them by each other. Okay, number of degrees of freedom is a property of the molecule, so that cancels. Boltzmann constant cancels. So what you get is E final over E initial equals T final over T initial. Okay, T final, the temperature has been raised to 150 Celsius, which is needing to be converted to Kelvin. And the initial temperature was 50 Celsius. Okay, if I compute what number this is, this gives me 1.31. Okay, so the initial energy was given by the variable K, or sorry, not the variable, like this fixed constant number. Maybe I should call it K sub naught or something. So the final energy has increased as we expect by a factor of 1.3. A little bit of a non-intuitive problem. There isn't really, okay, well, I guess I didn't have the answers written out at the time of making this. This is how I'm making the answer choices. But if you see a ratio or you are told the initial temperature as a variable, using the division by itself trick is probably pretty smart. Okay, this problem looked a little strange to me, so I don't really know why I left it in here, but let's see. Okay, the gas is trapped below a piston, and presumably there's air on top of it too. So the gas is holding up a fixed volume of pressure, or sorry, a fixed amount of pressure, because it's holding up a fixed amount of weight. And we're going to cool the gas, and the whole idea is that the gas is going to shrink and get compressed until its pressure rises back up to whatever is necessary to hold up the same amount of weight. So the initial pressure and the final pressure are actually going to be the same number. Okay? Now the volume is changing and the temperature is changing, but the pressure is constant between the initial and the final. Yes, it'll change slightly, but if you cool it down slightly, like slowly, the pressure will pretty much stay at the same value the whole time, so it holds up the piston almost entirely. So this is actually a constant pressure process, which means Charles' law applies. I'm going to put constant in quotes because, again, technically, the pressure will be only a tad bit lower than equilibrium as long as you're slowly cooling the gas down. The piston will slowly move downwards, and the pressure is pretty much able to hold it up. It's only lower by a tiny bit. Okay, the volume of a cylinder is pi r squared height. We're assuming the radius doesn't change. Okay, so the pi r squareds actually cancel. And what we get is that height final over height initial is T final over T initial, right? T final is 107 Celsius, so I guess actually the piston is going up. Remember, we need to convert to Kelvin. Okay, and this gives us a number of 1.27. Oops, sorry, and this is equal to, over here, height final over height initial. And does this make sense? Yes, we increased the temperature, so the height increased, right? The gas expanded a little bit. One thing I should have mentioned at the beginning is, since I saw this word ratio, in addition to sort of having to reason about that the process was constant pressure, I was sort of really directed to the like either Boyle's law or Charles' law because that's how those are derived as ratios of the ideal gas law divided by itself. So again, whenever you have this word ratio, you probably want to divide the master equation, which is the ideal gas law, by itself. And that's like where Charles' law came from. So this is actually a really clear pathway that we should try and use this equation. Also worth noting that this variable m was a distractor. Didn't actually need it. All right, we're talking about linear expansion here, and there's only one real equation, so this is a plug and chug. Okay, we know every number but one. So we are trying to compute delta L, and just as a reminder, this is like the original length right here. Okay, the original length is 1,000 meters. Alpha is 1.1 e minus 5. And delta t is negative 40, right? T final was 0 and T initial was 40, so you have 0 minus 40. And if we plug all these in, we get negative 0.44 meters. So the original length was 1,000 meters, so the final length is 1,000 minus 0.44, which gives us 999.56 meters. So the bridge shrunk by about a foot. Okay, let's see. We have the keyword constant volume, so isochoric process. We have the keyword monoatomic and also ideal gas, so we know specific heats when we need it. Okay. I should probably say, let's see, there's a couple ways you can attack this problem. I should probably say heat energy here. Let me just mark this down as notes. Okay, so the first law here is going to simplify a lot because we're in a constant volume. When you're at a constant volume, work done is 0. So the first law loses that W. And it's always a good idea when you have the first law to replace delta E thermal with NCV delta T. And we can just check if we know every variable in this equation. Also, I'm going to replace delta T with T final minus T initial. All right, Q in is negative 831 because heat is removed. N is the variable we're looking for. CV for a monoatomic gas is 3/2 R. T final is 405. T initial is 455. So I can move all this stuff over to the other side. And if you compute this number and then divide negative 831 by it, you get N equals 1.33 moles. So again, sort of the hint here was that we talk about heat removal, and we're told constant volume, which means, heat removal means you got to look at the first law probably, and then constant volume means that the first law simplifies because work in is 0. So you have this nice, easy first law. Okay, let's see. We have piece of aluminum being dropped into water, and we're asked about finding the specific heat of aluminum. Usually you go in reverse, you're given it and you ask the final temperature, but here we go. So let's see. We assume that there's no boiling or melting going on because the equilibrium temperature is 30 Celsius, not like 200 Celsius. Sometimes if you put a giant chunk of aluminum, the final temperature would be over 100, but it's not. So all the heat changes that go on, we have the water increases in temperature. The aluminum decreases in temperature, but remember, for MC delta T in these calorimetry problems, they already automatically come with the correct sign because delta T will automatically be positive or negative. And all the total heat flows had better add up to 0. And let's just identify our variable that we are hunting for, and we know every other number in this equation. So let's see. Mass of water is 380 grams. C of water is told to us in joules per kilogram Kelvin, so I'm actually going to make this into kilograms. Okay, delta T water. T final of the water is 32. T initial of the water was 16. Okay, aluminum, I'm going to do the problem in kilograms, so we have 0.08 kilograms of aluminum times our unknown variable. Delta T for the aluminum, the final temperature, right, this is T final minus T initial. The final temperature is 32 because the whole system settles there, and the initial temperature is 495. Okay, if I plug all these numbers into my calculator, this first term here is 25475. This next term is negative 37.04 times C of aluminum. So I move this to the other side. I divide 25,000 by 34, or by 37. And I get that C of aluminum, and I did the mass in kilograms, is 687.8 joules per kilogram Kelvin. All right, we talk about heat removal from a gas, so probably first law. Okay, other keywords, held at constant volume, which means that work was 0 because the volume didn't change. As usual, it's a good idea to replace delta E thermal. Oh, wait, actually, this problem is a huge distractor. I actually think, did I make this question twice? I think this might be the same question as before. Did I? On slides 14, slide 6. Yeah, I guess it's kind of a clone. So I actually don't really need to do any work because the work done on the gas during the process is 0 for an isochoric process, right? Volume doesn't change, so this problem's done. I think it's a repeat of another one, but it's good to be aware of that. Okay, here we go. How much work does the gas do on its surroundings? And we talk about heat removal, and we have this other keyword, isothermal. So heat removal tells us, first law, certainly going to be where we want to start. Okay, the process is isothermal, meaning T final is T initial, delta T is 0. So this delta E thermal term, which is like NCV delta T, this actually is 0. Okay, 5 joules of heat is removed, so Q in is minus 5. Okay, this tells us that if we move the 5 to the other side, that work in equals plus 5. So the gas had work injected into it. So the work by the gas on its surroundings is -5 joules. Right? The whole problem, the whole first law tells us the work done on the gas, but the question asks us how much work does the gas do on its surroundings? Right? So if 5 joules of work were done on the gas, it absorbed work from its surroundings. It didn't do work on its surroundings. So the work outputted was -5 because the gas was actually the recipient of the work. Okay, we talk about ratios here and an isothermal compression, which tells us that probably Boyle's law is the way to go. Okay, P final, V final equals P initial, V initial. We're asked about the ratio of V final to V initial, so I'm going to move V initial to one side, and I'm going to divide P final over to the other side, being very careful not to flip letters. Okay. The ratio of final pressure to initial pressure is 4. That means this right here is actually 1/4. So the answer is that VF over VI equals 1/4. And let's just check, does this make sense? The final pressure is 4 times as big, so the gas got squeezed down. So yes, it makes sense that the final volume is smaller than the initial volume. Okay, some key words here. Isothermal, well actually I suppose let's just read the question. Find a change in thermal energy of the gas during the process. So we have two kind of weird conflicting things, constant pressure and constant temperature. I actually don't even know if this question is possible, so I'm going to have to probably tweak it a little bit in the real it's kind of hard to hold two variables in the ideal gas as long as you're fixing n. You're actually fixing 3 variables, so the third one can actually change. So this problem was kind of typed wrong. So I'm probably going to eliminate this statement in the real exam. So a gas is isothermally compressed. Isothermal tells us that delta T was 0, and we're asked about the thermal energy of a gas, which is a hint that we should be looking at this equation. Okay, but delta T is 0, so delta E thermal is also 0. Another sort of trick question. Okay, this is going to be about the area under the curve representing work, and we're just going to need to be careful about the sign, and we'll check the sign at the end just to make sure we didn't do anything wrong. So work is the negative of the area as long as it's going left to right. However, in this case, we actually have a right to left graph, so we're going to end up with a positive number because the variable area is negative, and we have to take another negative of that to get the work. So the height is in atmospheres right here, so I'm going to quickly convert. Into pascals. Okay, the area of the triangle is 1/2 base times height. The base is, how big is this? 0.08. And obviously each of these heights here is 1 atmosphere. So the triangle has area 1/2 base, so 0.5 times the base, which is 0.08, times the height, which is 101,300. And I'm going to add on the area of this rectangle, which is just base times height. So 0.08 times 101,300. And I get the work done is 12156 joules. And I got a positive number as I wanted because the gas was being shrunk from a large volume down to a small volume. It was being compressed. So work was being done on it. Okay, immediately I see find the heat inputted during the process. So this is definitely a first law question. Okay, it expands isobarically. Okay, so whenever I see isobaric in my handy dandy equation sheet, first law section, it says when it's isobaric, the none of the variables is zero. Like if it were an isothermal, delta E thermal would be zero, or if it were adiabatic, Q would be zero. Um, Isochoric, W would be zero. When it's isobaric, none of them is zero. However, work in is just equal to negative P delta V. You don't have to do any integrations. So the first law definitely simplifies a bit. So let's see if we actually have enough to do it. As usual, delta E thermal, we probably want to replace it with N CV delta T. And let's see if we actually might know every variable in this equation. Also keeping in mind we have a monoatomic gas, meaning that we actually know CV. Okay, let's see. Find the heat input. So Qn is our variable. Let's see if we have enough pressure to solve. The pressure is 3 atmospheres the whole time, so that's done. Delta V is told to us, so that's done. CV is told to us, so that's done. Let's see, can we find, all right, let's replace delta T with T final minus T initial. Okay, we are told T initial is 373, so that's done. All right, now here's where you kind of have to play around with it a little bit. This is a tough question. Might make this the extra credit, to be honest. It looks like we're stuck because we have 3 variables. We don't know N, we don't know the final temperature, and we don't know heat in, which is our actual variable. So we need to find a way to find T final and N. So we look to our list of emergency ripcords when we don't have enough, we have too many variables, see if we can solve some more of them. And the very first thing on the list is try and apply the ideal gas law to the beginning of the process. See if you were told 3 of the 4 variables. And in this case, we're told the initial temperature, pressure, and volume. So we actually can find N, which is the last thing in the ideal gas law. Okay, PV equals nRT, so N is PV over RT. And obviously we're doing this at the beginning, so we use all the initial stuff. Okay, if I plug in numbers, this tells me that N equals 0.01. It's 0.009. I'm going to round to 0.01 moles. Okay, so I actually know that. So N is good now. And all I need is T final. Let's see if I can apply the ideal gas law to the end now. I don't know T final. So this is my little variable. I'm trying to solve the big problem, but first I need to find T final using the ideal gas law. I know N. I know the final volume. The final pressure, it's isobarically expanded at a pressure of 3 atmospheres. So I do know every variable except T final. So T final is P final, V final over NR. Okay, P final is still 3 atmospheres. V final is 200 E minus 6 and divided by the number of moles times the gas constant. Okay, and if I actually do this computation, get T final is 732 Kelvin. Okay, so now I'm finally in a position to plug all my numbers into this equation. Okay, so I have 0.01 for N. Monatomic ideal gas is 3 halves R as its CV. T final, 732 I just found. T initial was 373. I'm going to move P delta V over to this side, so my expression is equal to Q. Pressure is 3.04 E5. V final is 200 E minus 6. V initial was 100 E minus 6. Okay, and this is equal to Q. So if I plug in all these numbers to my calculator, I get Qn equals 75 joules. Again, sort of the hints for this process led us pretty effortlessly to this point, and it was just a matter of pulling the emergency ripcord of ideal gas law on the beginning and end when we realized we might be screwed. Okay, but you could hear the uncertainty in my voice because I hadn't done this question before, and I just had to stay calm and go through my checklist. Okay, tough problem though, but it's about a full strength thermo problem. So if you got this one or you now understand it after I've explained it, kudos. Okay, this is a traditional calorimetry problem. We have hot copper being placed into cold water. Oops. Got an Among Us sort of thing there. Okay, I think we assume that the copper is not big enough to melt this much water, boil water, so let's just assume that for now. And if we find the final temperature is greater than 100 degrees for the water, then problems will happen. As usual, we just add up all the MC delta T's for every object involved. And they automatically come with the correct sign. Delta T will automatically be positive or negative depending on which temperature is greater, so no extra signs needed. All right, and let's check if we have everything in this equation. All right, well actually first I should replace delta T for each object with T final minus T initial. So T final copper minus T initial copper, and T final water minus T initial water. Okay, and let's count variables here. I'm told everything about mass and C. I'm told the initial temperatures, and it looks like I'm screwed because I have two unknown variables, the final temperature of copper and water. But they must reach the same temperature when they come to equilibrium, otherwise they'd still be, giving heat to each other. So these are actually the same variable, which I'm just going to call this red variable T. Okay, so now it's just a matter of plug and chug into this equation. So let's see, mass of copper is 0.04. C of copper is 385. T initial for the copper, I'm going to do everything in Celsius, is 330. Mass of water is 0.15 kilograms. C of water is 4190. And initial temperature of the water is 20. Okay, now this is going to be a little gross to solve. I guess I'm just going to, find this number and, distribute it. I'm going to have to do that on both terms. It's going to be a little gross. But it's important to know how to do this in principle. Okay, so this number right here is 15.4. So the first term is 15.4 T minus 5082. Okay, that's from foiling that. Okay, now on to the second term. This number right here is 628.5. Okay, now I combine these two, right? It's like 2t plus 3t equals 5t. So 628.5 plus 15.4 gives me 643.9t. Now I'm going to combine the two constant numbers, 5082 and 12570. Okay, now I move 17,000 over to the other side and divide through by 643.9 to get t. And I get t equals 27.4 Celsius. Again, an important part of this question was recognizing that the copper and the water must reach the same final temperature, sticking to your guns, writing out the equation, and realizing it's just one variable appearing in two places, so you're actually definitely able to do the problem. Why did I make myself and you guys do so many of these? Okay, you have an ice cube that is going to melt in the coffee and then further cool down. So there's going to be an extra latent heat term, which is one of the things I said on one of the first slides. When there's a phase change, it's not just the MC delta T's, there is plus or minus a latent heat. So we have three heats going on here. We have the latent heat of fusion, of ice melting. And we need to be careful if it's a positive sign or a negative sign. Now, in the equation sheet somewhere, in calorimetry, I tell you what you should use. I'm going to need to look it up myself. I have plus sign for melting or boiling, minus sign for the other direction, so freezing. Here we're melting, so we have a plus sign. And then, as usual, the other MC delta T terms don't need any sign adjustments. They automatically come with the correct sign if you just use plus signs in front of them. Okay, so here's MC delta T for coffee, here's MC delta T for water, and here's the term coming from the fact that the ice is melting. Okay, and let's just count variables. All right, we're told L, we're told mass of ice. The mass of water after, this is from the ice, after it melts. Okay, that's equal to the mass of ice, so it's still 12 grams. T final of the water, this is the unknown variable. And just like in the last problem, the coffee and the water after the ice has melted must reach the same final temperature, otherwise the system would not be in equilibrium. Therefore, we actually only have one T for both of them. There's not two separate T finals. Okay, we're told T initial of the water, we know the mass of coffee. Coffee is assumed, I suppose I should write this in the hints. Coffee is assumed to have the same specific heat as water. Okay, so we know every number but one in this. And this time, since I showed you how to do it the last time, I'm going to plug it into Wolfram because I don't feel like solving, to be honest. All right, latent heat of fusion for ice is 333 joules per gram, and the mass of ice is 12 grams. Mass of water after the ice melts, we assume it's also 12 grams. C of water is 4.2 grams per Kelvin. T is our variable. T initial for the water is 0 degrees because it comes from ice. Right? Immediately after ice melts, the water that comes out is just barely at the freezing point, so it's at 0. There's 200 grams of coffee. Again, C for coffee is, because coffee is basically water, it's just water, so you use 4.2 again. T is the variable, and T initial for the coffee is 85. So now I'm going to plug this into Wolfram. if you guys don't know, Wolfram alpha is really strong. And it can solve equations without having okay, and I plug into Wolfram. Less me, I guess. And it tells me the solution in an exact fraction. Okay, I get t equals 75.7. And I did all my temperatures in Celsius, so my final temperature is in Celsius. Okay, adiabatic process means you should probably be talking about the first law. Also, we see like delta E thermal and stuff in here. So I'm just going to write the first law. Okay, the meaning of adiabatic is that Qn equals 0. Therefore, delta E thermal equals work in. Not really much more to say about that. Just remember, adiabatic means Qn equals 0, and it's almost always a hint. If you see delta E thermal, adiabatic, and or work in one sentence, you should probably be using the first law extra hard. Okay, let's see. We have an adiabatic compression going on here. So for adiabatic compressions, the way you find like the relationship between the final pressure and initial pressure is by using this P V to the gamma version of Boyle's law. Right? For Boyle's law, that's for isothermal processes. Adiabatic and isothermal are different, so you have to use a different equation. And we have another key word here, diatomic oxygen, which tells us the value of gamma. Scroll down and find it. Gamma equals 7/5 for diatomic. Okay, let's just see what we can do here. Final volume, let's see, do we know the initial pressure? Yeah, 2 atmospheres. Do we know the initial volume? Not really yet, so that could be problematic. Let's see. We're asked about the final volume. Okay, so this is our real variable, so we're going to need to figure this out if we want to get something. The compression goes until the pressure is doubled from 2 atmospheres to 4 atmospheres, so we know this. So if we can find the V initial, then we'll actually be able to find the variable we want. As usual, our first step in our emergency ripcord is check if we can do the ideal gas law. We know N, P, and T at the beginning, so we can find V at the beginning. Okay, 0.6 moles. T initial is 150 plus 273, right? We need to be in Kelvin. Over the initial pressure is 2 times 101, 300. Okay, points. I'm going to plug this in my calculator. Okay, and I get V initial is 0.0104 meters cubed. So now I can plug everything into this equation. I'm looking after that red variable VF, so let's just see if I can get it. All right, P initial is 2 atmospheres. V initial is raised to the 7/5 power. P final, I'm going to move it over to the left-hand side. It's double the initial pressure, so 4 atmospheres. Okay, and this equals V final to the gamma. So first I'm just going to compute the left-hand side, and then we'll get rid of the power. The 101 3000s cancel. Remember to, actually I'm going to write this down, come choke. Make sure to put gamma in parentheses. If you do to the 7th power and then divide by 5 after, your calculator doesn't know what's going on. Okay, 2 times that to the 7/5 divided by 4 gives us VF to the 7/5 is 0.0008. Okay, and now I'm going to take both sides to the 5/7 power. Right, you multiply exponents, so these two actually will cancel to 1. Okay, so I take my answer, I raise it to the 5/7 power, and I get V final is 0.006. Okay, now I'm asked about, that's final volume, I'm asked about the final temperature. I could do the TV to the gamma minus 1 equation, or I can use the ideal gas law at the end, because I know the final pressure is 4 atmospheres, I know N, and now I know the final volume. So to get the final temperature, I can do PV over NR. To get T final, right, that's just the ideal gas law. P final is 4 atmospheres. V final, I just found, is 0.006. And then I divide it by the number of moles, which is 0.6 times the gas constant. And I get T final is 487.61 Kelvin. So remember, the ideal gas law puts out temperatures in Kelvin. Okay, heat input means we should probably be looking at first law. Okay, second keyword, isothermal compression, means delta T equals 0. Since delta E is just NC delta T, that means this is 0. So the first law is just that Qin equals negative work in. Okay, we have a compression going on here, so the work in is a positive number. So the heat in is therefore a negative number. Okay, here we are given a lot of information. Keyword, adiabatic compression, and we're asked to find the heat input. Adiabatic means 0 heat was inputted, so there's actually no work in this problem. Another one, I don't know why I put so many like trick questions in here. It's kind of, it's not really, it's like free points, but don't know why I'm putting so many of these distractor questions. It's I guess just be aware when the real test comes around. If you see 0 as a possible answer, it's worth reading the question kind of carefully and just seeing if you actually can skip all the work. Okay, heat conductivity problem, there's only one equation, so this is probably going to be a plug and chug. Let's see, we're trying to find the rate of heat flow, and the equation is already built to tell us that. Okay, K for concrete is 0.8. The area is 1 meter squared, so there's 1. Delta T is 100 degrees, right, the temperature difference between the edges. And the thickness, do I not tell you the thickness in here? Yeah, I need to tell you the thickness. Let's say the thickness is 2 meters. Let me just mark this down on my corrections real quick. Okay, so L, remember, is the thickness, so 2. So if I plug all these in, 0.8 times 1 times 50, oops, 50, which gives me 40 joules per second. Okay, engines. Draw the diagram. Don't ever skip it. We'll keep our coloring. We have our hot reservoir. It pulls 800 from the hot reservoir. It exhausts 500 of waste heat. So that actually allows us to complete the diagram. Okay, and efficiency is work out over Q hot. So I get 3/8. Again, our equation had this form either work out over Q hot, and we actually derived an equivalent form by using the engine diagram to get 1 minus Q cold over Q hot. But at any time you have two of the three variables, either Q hot, Q cold, or work, you already know the third, so you don't need to panic if you don't have the exact two variables you need. Just draw the diagram, that'll let you find the third, and then you can plug it into whatever form of the eta equation you want to. Okay, refrigerator, gonna be drawing a diagram again. Okay, 100 joules of heat are pulled from the hot reservoir, or from the cold reservoir. An unknown amount is exhausted to the hot reservoir, and an unknown amount is, put in as work for a refrigerator. Okay, what we're told, however, is the coefficient of performance is 5, and the coefficient of performance tells us, I believe it's Q cold over work hot. It's Q cold over work in. So we're told Q cold is 100 and K is 5. So this tells us that work in, if we move variables around, is 20. Now from our picture, we see the work in and the Q cold combined to Q hot of 120, and that's the answer. Ideal efficiency means you use the Carnot formula, right? That just tells you how efficient is the perfect engine operating between two given reservoir temperatures. Real engines, if you compute their actual work done and stuff, because they aren't a perfect cycle, they're not going to be as perfect. In the case of a perfect engine, it's 1 minus T cold over T hot. However, we need to work in kelvins, otherwise the problem will trip us up. T cold is 20. T hot is, T cold is not 20, it's 20 plus 273. And if I plug in numbers, I get the efficiency is 0.621 for a perfect engine. A real engine might be told you to have 50% of this efficiency. In this case, the efficiency of your engine is 0.31, and then you can finish the problem pretty easily, like we did in the last problem. And speaking of that, here is literally exactly the same sort of deal, where you are told the efficiency of your heat engine indirectly as being 60% of the perfect efficiency. So the perfect efficiency would be 1 minus T cold over T hot. Again, need to convert to Kelvin. So the perfect efficiency would be 0.652 or 0.653. And your engine doesn't have this efficiency. It has 60% of this. So the actual efficiency is, multiply the answer by 0.6, gives you 0.392. Okay, so this is your engine's actual efficiency. All right, now let's draw an engine diagram. Okay, work at would be 1,000. I actually don't think we'll need the engine diagram, but it's good to have. So we're told eta is 0.392, and we know eta is work out over Q hot. Work out is 1,000, so we can just move Q hot to the other side and 0.392 to the other side. And we get 2552 joules is extracted from the hot reservoir. And we can sort of like go backwards and check. If we compute the efficiency of our engine, it would be 1,000 over 2552. And if you compute that, you get 0.392, which is 60% of the perfect efficiency. The efficiency of your engine was lower than the perfect efficiency. Okay, find the efficiency of the engine. We're drawing a diagram. It's like I'm a broken record. Okay, we have two heat inputs going into the gas. So these are coming from the hot reservoir by assumption and being put into the gas for a total of 300. And 150 is being blown off as excess exhaust heat to the cold reservoir. So we can say that we have 150 joules, therefore, of leftover heat being used as useful work. So the efficiency is work over Q hot, which is just 1/2. Okay, and I added these sort of last second because I thought it was important to remember. Let's see, we can kind of weed through them. I'll just tell you right now, choice D is not going to be it because one will turn out to be true. Choice C, this statement that there's no difference is absolutely wrong. E thermal and Q in are not the same thing. For solid objects, they might turn out to be, but for gases and stuff, right, you have this first law actually, delta E thermal is Q plus work. So they're only the same when work is 0. Right, so in general, they are not the same thing. Okay, this one up here, A, it turns out it's just, not right. The equation delta E thermal equals mCv delta T, counterintuitively, is actually always true. Okay. And then in order to find Q, you would have to use the first law. But delta E thermal is always equal to mCv delta T, even if the process is not constant volume, which is kind of dumb, kind of counterintuitive, but it is the reality of the situation. The reason for it has to be with the definition of Q versus delta E. Why does it work when the process is in constant volume? It has to do with the definition of like what variables you hold fixed during a process. And if you study advanced thermo, it'll be pretty trivial, but we don't really have the technology to deal with it here, so not going to do it. Okay, and adiabatic processes. Let's see. Adiabatic process, just a reminder, it means the temperature inputted, or sorry, not temperature, but the heat inputted is 0. Let's just write out the first law because I see a lot of things about like thermal energy and temperature of a gas here. So I'm just going to write out the first law just in case I don't know if I'm actually going to need it, even though I wrote this problem. All right, heat inputted during adiabatic gas is 0, so it certainly doesn't depend on temperature change, right? It's just always 0. Temperature of a gas does not change during an adiabatic process. That is not necessarily true, right? Just because Q equals 0 doesn't mean delta T, which is contained in there, is 0. It just comes from work rather than heat. So C is definitely not right. The work inputted during an adiabatic process is always negative. No, that's not right either, right? The work inputted could easily be positive if delta E was also positive. So this is certainly wrong, which leaves us with B. So let's just double check that this is correct. The temperature of a gas changes during an adiabatic process as long as the work done is not 0. So this is saying that if work is not 0, delta T is not 0, which is definitely true. Okay, so that's why B is the correct answer. All right, looking back, this is definitely a more aggressive practice test than the previous one, so I'll try and tone it down a bit for the real thing. Just really commit to writing down somewhere your list of emergency procedures when you aren't really sure what to do on a problem. I think I outlined them decently clearly, and I think I was pretty pedantic about underlining all the key words that I saw in each problem, and that's sort of the way that I want you to approach these problems. Look for the key words to sort of snap to the appropriate 2 or 3 equations that might actually solve the problem. And then if you get most of the way through a problem, remember there's always like those one or two like emergency, maybe I try the ideal gas law, maybe I will want to do a ratio of equations that you can always try to use. And of course, don't try and skip steps, draw the diagrams, draw the heat engine diagrams. And yeah, I think that's pretty much all I gotta say. So feel free to show up to office hours, ask me questions, and I will see you at the real thing and at the review session.